The second part of this section is about the exponential decay, and this is very similar to the exponential growth, so hopefully we'll be able to go through it pretty quickly. Exponential decay is just like growth, except your base value is going to be slightly different. In growth, remember we said that the base was larger than 1, but in decay, your base is going to be between 0 and 1. So it'd be important to remember that your exponential decay functions are going to have fractions for their base. And then we can just go ahead and graph. I've got an example here to start with. Notice that my h value is 0 and my k value is 0, so this doesn't shift left or right, and that also means that my asymptote is going to be at 0 here, so I can draw that horizontal line in, and then I can go ahead and plug into our table. So make your table, and we'll plug in some values for x and y. So if I plug in, we'll start with 0 all the way up to maybe 3 or 4. If I plug in 0, I'm going to get 1. I plug in 1, I get a third. Notice I'm going to go through this pretty quickly, so if you have any questions about the numbers, let me know. If I plug in 2, I'm going to get 1/9. Always leaving them as fractions is very helpful. Okay, if I plug in 3, notice I get 1/27. So this is going to be getting smaller and smaller as I go to the right. So what that means is I should probably plug in some negative numbers. And so I can change my -4 to a -1. So if I plug in -1, my fraction is actually going to flip and become +3. If I plug in -2, it's going to flip and become +9, so way up there. And then I can stop because I've got at least 5 points here, and I can connect them. And there's my exponential decay function. And remember, cannot cross your horizontal asymptote. I'll put A there for asymptote, and then you'd be finished. The only other thing they might ask for is domain and range here. Same concept, domain will always be all real numbers, and you can write it either way here. Okay. And then your range is going to be above the dotted line, so that will be y is greater than 0, or you can write 0 to +infinity in your parentheses. Okay. If you have questions about the points or the domain and range or the asymptote, please make sure you ask me in class. And now we're just going to do an application problem, and then we'll be done. This application problem is very useful, especially if you're talking about in general your body and processing different things, whether it's caffeine or if you take a medicine, your body will process that medicine and eliminate it slowly over time. And so decay can be very good in application. In this example, it says a cup of green tea contains 35 milligrams of caffeine. It says the average teen can eliminate approximately 12.5% of the caffeine from their system per hour. So what we want to start off with is coming up with an equation to represent this scenario. Then we're going to draw a graph, and then we're going to figure out roughly how much caffeine would be left in this person's body after 3 hours. The formula we use, because we've talking about percents and amounts, is going to be the formula from the last video. So we'd have the amount is going to be our initial amount times 1 plus our rate to the t power. And so all I have to do is plug in my information. So I know my initial amount was 35, so that's our little a. So we'll write a of t equals 35. We know 1 is always going to be there, but then we know it's going to be 12.5%, but it's eliminating this. So this is actually, instead of plus, is going to be subtraction. And that's important when you're talking about decay, that you make sure you're subtracting instead of adding. Okay, so I'm going to have minus our decimal 0.125 and then to the t power. So if I simplify that down, I'd have a of t equals 35 milligrams and then times, and if I subtract that decimal, I get 0.875 to the t power. So there's our formula we want, and now we could use this to create our graph. Our graph is going to be in terms of time, so this is going to be in years, and then the amount of milligrams of caffeine that we have in our body. And this time maybe we count by 5, so 5, 10, 15, 20, 25, 30, 35, okay? because we know at the start we have 35 milligrams. So if I make my table, I know T and then A of T. I'm going to have at 0 hours, I have 35 milligrams. That's what it is when you drank the caffeine in the tea. Then I could go ahead and plug in number of hours that have passed. Whoops. So if I plug in here 1 and maybe 2, all the way up to 3 or 4 or 5, it really doesn't matter. Enough to get your points. I can plug into my formula that I've gotten. Remember, you always do exponents first. So I'm going to take 0.875 to the first power and then times 35, and that gets us 30.6. Then I could do the same thing, plug in 2, so 0.875 squared times 35 gets us 26.8. Do again, plug in 0.875 to the third times 35 is 23.4. And if I keep going, I can fill in the rest of this table and get, whoops, let's see here, 20.5. And I believe this one is around 18 point something, okay? So now you can plot your points, make sure you count the year or the time, so 1 hour, 2 hours, all the way through. Obviously, if you have grid paper, that would be definitely the more accurate way of doing this. Make it a little bit easier to tell where everything goes. But when I plot my points, this is roughly where, oops, that should be up a little bit, my points will be. And then lastly at 5, it's around 18. So notice my amount of caffeine is decreasing each hour, which it should be. And then you could look at your grid or your table and determine how much you had left in your system after 3 hours. So after 3 hours, there was 23.4 milligrams of caffeine left in their body. Okay, so great application. This works anytime you've got a percentage and an amount of time. Just make sure you pay attention to if it's growth or decay, because that will determine if you add or subtract your rate. Okay, any questions, let me know, but that's it for today. Thanks for listening.